Good morning, everyone. Welcome to the first Monday session of the last week of the CHPC NITheP summer school. And we're very happy to have Christine with us, who will continue her story into the statistics with R. Christine, it's all yours.
Thank you so much. So just running a poll at the moment, what you guys got up to this weekend, just to get everyone logged in on the polling software. We're going to do a more serious question just now. So today we'll quickly go back to last week's questions, the homework I gave you, just to find out if there's any questions there, if anyone figured out the challenges I set, and then we will look at distributions. So distributions and statistics are quite important. And yeah, I think our poll time has run out. So let's get going with that. So questions about last week. Before we start, feel free to switch your mic on. You can type in the chat as well. Anything that you guys are unsure about with the descriptive statistics still, or can we move on to the new work? I am keeping an eye on the chat, but you're also welcome to just switch your mic on. And just for interest sake, also feel free to let me know in the chat how you're finding R so far. Is it easy? Is it challenging? Yeah. Doesn't look like we have questions, so we can move on to the homework. So I left you with a few challenges to look at. So the first one was to see if you can figure out with these plots, specifically this last one, whether you can fill these different plots with different colors. So I'm just going to run this code again. Oh, wrong button. I haven't loaded ggplot. Let me just load my library. So you can see R tells you very quickly if there's an error. It tells you what the error is, and you can normally figure out what you've done wrong. Usually it's not R that's wrong. Usually it's the people. So if we rerun this code now, it should work. And we have these violin plots. Now, the challenge was to see whether you could fill these plots with different colors. So could anyone manage to do that and figure out where to add what code? You're welcome to add it in the chat or just tell me yes. Oriyomi, you had your mic on? Any ideas? Did anyone try to do this? Or was the weekend a bit too busy? No volunteers yet. Okay, so I'll show you this one. So it's actually quite easy. All you have to do here is just add full equal to, and just tell it which variable to use. So we can do it on gen health, if I'm not mistaken. And if I do that, you'll see that it automatically changes the colors. It puts a fill for each of these graphs. So like I said on Thursday, the word full, I actually gave that hint, and that's how you would do it. So you can go and adjust these colors. I will add something on Moodle, a document which gives you an idea of all the different colors you can find in R, and how to approach colors. So I'll add that later on. But yeah, it's quite flexible. You can specify the colors yourself, or you can let it, in this case, define the colors. You can also set a color palette beforehand, and that will then be applied when you don't have to specify for each of these options what color to use, but if you specify the color palette, it will go and look at that color palette and apply from there. So that's just a simple extra thing that you can be aware of. Then the next bit of homework I gave you was to finish off this exercise. So I gave you a hint about how you can do the plot. And your homework was to figure out firstly, how can you do the title? And by making use of these variable names in each case. And then I said, use a for loop to go and do this automatically for all the different variables. So just need to set my working directory. I just realized I haven't done that yet. Otherwise, it's going to save everything in the random place. So I'm just going to set my working directory again so that when I export my plots, it will export to the correct place. So has anyone tried this exercise to do these scatter plots automatically using a for loop? Any ideas from your side? So we had this plot. So let's actually just, this is not in this data set. We said that we need to create this data frame. Fast food not found because I haven't loaded it yet. I'm in a new instance of R. So let's just do data fast. Oh, and it's not finding it because I haven't loaded the open intro library. So this is where I need to know where the data set is. Once I've loaded the data set or the library, then it doesn't matter. I can load the data quite, or yeah, I should be able to load it quite easily. Let's see if it works if I do it like this. Yeah, now it recognizes it. So I haven't actually had to import it specifically into R. It knows, go and check all the packages that are loaded and see if the data set is in there. If not, give me an error. And if it is there, it will go and open it. So I've done that now, and I'm going to just run that code. And then we said we did this plot. So that was my plot here. So the homework, first bit of homework, let's start off with the title. How would we do this? Now, even if you haven't done this, I want you to try and guess, how would we write this or write a title that shows us what variables we're dealing with. So let's say I want to call this scatter plot of something and something else. It's just a very short title now. So how would I automatically have those variable names in there? Any guesses? There's no guesses. I'm going to start randomly picking people who haven't spoken before. Yes, Martin.
Yeah, we can use the paste function.
Yeah, the paste function. Okay, well
Yes.
done. So yeah, so there's a paste function. And let's just put the brackets around it. And then how would I use that paste function?
So since we want to use the for loop function,
Yeah.
so I think we start by saying maybe for column,
Yes.
in what?
In
For column. So we can just create a list, right? So let's say for column in list 1 up to learn what? We want to use the length for columns, right? So we are going to have our data frame. It's FF. So if we say FF dot core names dot, is it dot core names or
okay, so in
core names,
Python,
it's core names, then FF inside the brackets.
Okay, so let's try that columns. I haven't actually used this column function.
Names.
Okay, so
it's called that the name. Call.
yeah, C-O?
C-O-L.
Yeah.
Then names, yeah, that one, that function.
This one that's highlighted.
Yes, it's
or
it's
that
a
one.
base function, yes. So if
That
you say
one.
call names,
Yeah.
then it gives us the names of our variables.
Yeah.
So, but we want the length of that one.
Yeah. So let's
So
just run the school names. I just want to see what happens when we use this.
All right, yeah.
Yeah.
Yes.
Okay. So yeah. So it does give us the names. Ah, cool.
Yeah.
Yeah.
So when you say length of that one, it will give you the number of the number of variables that you have.
Okay. So like this length of call names. Let's just see if I copy and paste that into our console. So that tells us there's 17 columns. So this is then basically this for loop. Yeah, we'll go from 1 up to 17. Okay.
Yes.
So and I'm just going to
we
move
are going
this
to take
into
that one. Yes.
Yeah. And just put it in there. Okay.
Yes.
Yeah. So this is one thing I wanted to point out just for the for loop, which is different from Python. In Python, you didn't have the brackets. You use the indentation to say where the for loop ended and started. Here we indicated with the brackets. So we can see everything that's inside these brackets will be in that for loop. So that's just something to take note of. Okay. So what next?
We now want to replace, right?
Yeah.
So yeah, we are going. Let's remove the other FF4 since we are now plotting a different plot for each column, right?
Yeah, we are.
So let's where there is 3, let's now replace that one with column.
Okay, but keep in mind that we want to go and do each plot. So we want to do calories against cal fat, then calories against total fat, then calories against saturated fats, and so on. So that 3 we actually want to keep each time because it's going to be the same in all of the plots. It's the second variable that we want to change. So it's that FF4 that we want to change.
So I think, in that case, you may now need to for loop twice, right? Since we want.
Yeah, I think there's a simpler way to do it, though.
Yeah, so that one I think is now a longer route.
Yes, I think this is the longer route. So I think we want to do the simplest thing possible. So I think what we want to do, and I like your approach so far, but we want to think, what do we want to work through? We want to start actually at column 4. So we want to always have column 3 and then start from column 4. So I'm going to change that 1 there to a 4 because we don't need to loop through the first 3 columns. And then
no, it's fine.
Yeah. So then this will go all the way to the last column, which is the salad one. And remember, if we go back to, I'm just going to open this so we can view it quickly again. If we view this, that salad column is actually not a numerical variable. So we don't want that one. So how will we adjust this code so it doesn't go all the way to that one?
Subtract 1.
Perfect.
Yeah.
So we're just going to say here -1.
Yes.
And then it's overwriting my brackets, but there I have all of my brackets. So it's going to now start from column 4 and go up all the way to column 16.
Yeah, but I think there's an error there because minus 1 is supposed to be after that other bracket.
Yeah.
So that
let's test what happens so far. So I'm just going to comment this out, and then let's say we're going to just print and see if it works. Sometimes I know with R it doesn't always want to to print the while you're in a for loop. So let's see if the print function solves that. So I'm just going to say that ff names that we created, I want to see what it's looking at. So I'm going to say ff names, and then we call this column. So if we run this code, it says non-numeric argument to binary operator. So let's see, call names. Ah, yes, you were correct. That was one bracket too soon. So if we do that, there we go. Okay, so it's printed those, and we can say it goes all the way to calcium, which is what we wanted. So it started calfat, entered calcium. So the loop is now fine. We know the loop doesn't have any issues now. So now all we need to do is figure out the actual plot. So yes, so this one, all we would do is change this to what we call that. But we maybe don't want to type column each time. So let's actually just change this to an I. So I'm going to change that to an I. So this will now go through and it will create a plot each time of these things. And then we need to just put the label. We need to correct that as well. So if we run this, you'll see that it has gone and created a whole bunch of plots for us with the different variables. Our Y label does change each time. Title is still the same everywhere. Cool. So we've done most of the work now. So now the last thing is the title. How do we use that paste function to adjust the title?
So why don't we index? Since we are having core names FF, right?
Yeah.
So we know we are going to index that one. So it's going to be core names.
Okay. So I'm gonna just do that. Let's just put an extra comma. So call names and of FF, and then we're gonna index it.
Yes, yeah.
With an I. So let's see if this works. I've never actually tried it this way. Let's see if it does. It does seem like it's going to run into some issues. It says there's an unmatched bracket. So this bracket here does look like there's an extra bracket. So that starts us off. Yeah, it seems like there's somewhere an extra bracket. So this one matches that one matches that one. So that's fine. So you can see that R does show you which brackets match which ones. What happened is I have it automatically made 2 quotation marks. So that's why it ran into issues there. So actually, I think that bracket was supposed to be there. Yes, it was. Yeah. It was just the quotation marks that was the issue. So let's just run this code and see. So yes, it has now placed something there. But that was the second variable. Let's just say of, let's make that a 3 for now. And then we say, and that. Okay, so, and then we just copy this, but with an I for the index. Perfect. And that means that this, that I did here, this names one wasn't even necessary. You found a better way of doing it, which worked perfectly well. So yeah, if we run this, I've just changed that index now. We can run this loop and it should now give us for each of these plots, it gives us the title adjusted automatically based on which one we're doing. So I'm just going to remove those spaces because I see it doesn't set a space automatically in the title. And now it looks a little bit more normal. So then the last thing was that we said that we actually want to export these plots. So at the moment, what's happening is we're running this and it's creating these plots in the console. We wanted to export those plots into our working directory. So does someone else have any suggestions for how we can do that? It's actually quite straightforward. So all you actually had to do was take this code here. So you saw we used it here with ggplot, but we can actually use it with the normal plotting functions as well. So all you had to do was take this code. Let's say you wanted to do PNG images, and then you just put the dev.off command there at the end. So that means that it's going to create the plots, but it's going to, in this case, create plots using the same file name every single time. And that's not what we want to do. So we want to, again, use the paste function. And we can go paste something like this. So let's say we're going to put plot and then let's make it plot. And we paste the variable name. So I'm going to copy this again. This should work. And then we just paste that last little bit, the .png. And I think the issue is there's an extra comma. So somewhere I'm missing something again. Is someone seeing the mistake? I think there's the extra bracket. So there's the paste function. That should now be fine. That's always a problem when you edit code. So my working directory, I'm just going to open that. It's on my other screen, hiding. Okay, so there we have my working directory. So I'm going to run this code and then let's see what happens. I actually put this in the wrong place. So this PNG bit is going to move this. Should have been inside my for loop. I don't know why I put it outside the for loop. Blonde moment. Let's say it's Monday morning. So I could have just pressed enter there, paste that there, and the dev off also needs to just move inside this loop. And here, unlike with Python, it's not sensitive to the spacing, so it shouldn't cause any issues if you have an extra tab or something. Just want to try and keep it neat. So there we go. So I've run that, and if I now open my my working directory, you can see all of these plots were created automatically. So this is a very useful thing if you need to do multiple plots and you can use the loop to go and create those plots, then go for it. You can create names automatically. It makes sense that you can easily see what the plot represents, and that's it. So any questions about this? Or anything you guys want to know before we move on to the new work? Cool. See, Martin, you are happy. Perfect. Cool. Okay, so we've done the homework. And now I have another question for you. So before we carry on, I just want to know how comfortable everyone is with different distributions in statistics. So for example, binomial, normal, t-distribution, chi-square, Poisson, all of those different ones. I'm going to start the timer. I'm just going to pause it for a moment though. So I do want a bit more participation on this one. So go to ttpoll.eu and choose ID 74, and then you can just indicate there which option you are choosing. And as you have 2 responses so far. Okay, so I see not enough people, only 2 people answered, so I'm going to just restart this poll. Because it is important for me to know at what level to aim this. But for some reason, my remote doesn't seem to want to work today. Oh, there it is working. Perfect. Okay, so I see we have about 23 participants, myself, the lecturers included. Let's say we're looking for about 20 responses. I have 5 responses at the moment. Need about 10 more responses. I see we're still hovering around. Half knows what's going on a little bit, half doesn't know at all. Okay. Oriyomi, have you never done statistics before? There's still quite a few responses missing. Time is standing still. I think we need about 9 more responses. So while we're waiting for the responses, I'll just tell you a little bit about distribution. So people tend to be a little bit scared of distribution theory. I'm one of those people. I'm not like, I don't do distribution theory for a living. It is but it's useful. It's very useful. So with distributions, all it basically tells you, it's all in the name, is how things are distributed. So what kind of pattern do you expect to see in your data? So for instance, if I'm asking everyone how many cups of coffee do they drink per day, and I do a bar plot of the number of cups of coffee you drink a day, then we can look at that. Let's say the peak is at 2, then it means most people drink 2 cups of coffee a day. So by looking at that graph, you can kind of get an idea how the number of cups of coffee for different people are distributed for each day. And it just tells us a little bit something about the data. So some very clever statisticians years ago figured out that sometimes that pattern that we see has certain properties attached to it. So if you know that something follows a normal distribution, then you can easily work out the probability of finding an observation within a specific range of values. So it follows that probability will always be the same based on some other properties that we know. So we'll get into that just now. But yeah, it just basically shows you how values are distributed. So on this little crazy guy over here, you can see there's a peak and there's another peak. So something is happening around this value, something is happening around that value. We have less observations for the value over there. Where with the normal distribution, I think that's probably the most well-known distribution. Everyone knows that most of our values occur here around the center of the distribution, and then fewer observations will be found towards the tail end. So it's useful to think of these distribution curves kind of like histograms or bar plots, histograms most of the time. That just show you where you're going to find your observations. Okay, perfect. So I'm going to unpause this. There's still 8 people missing in action. But we will assume that they know what's going on then. Now with all of these distributions, yes.
Yes, I think I just noticed something with the poll. You expect the numbers to go up all the time, but in some cases the numbers were going down.
Yeah, it was someone who was pressing different buttons, skipping between different options. So yes.
So it's possible that some people might have put in, because I noticed in my case, if I click, I'm not sure whether I really clicked or not, because it doesn't tell you. So you click the second time, then it removes your
maybe that's the case. Yeah, I'm looking at here at the bottom, you'll see it says their responses, so that means 12 unique responses. Yes, that's how I know there's 8 people missing. So, but yeah, thank you for alerting me to that. Okay, so I didn't prepare a whole lecture on distribution theory. I kind of assumed that most people would have an idea of the basics, and I wanted to just show you the different distributions, just a basic idea how you can use them. So if you've ever heard of a p-value, that is something, then you've used a distribution most likely. You can, of course, get p-values with other techniques as well, but a lot of the p-values we calculate in hypothesis tests are based on distributions. So specifically, if you've done a t-test, it's based on the t-distribution. Now, we're going to look at a few different distributions today, not in great detail. I just want to point out a few small things with each of them and show you how, if you know what distribution to use, it's actually quite easy to do it in R. So my talk is more focused on how do we apply this in R. Now, the ones that I decided to just point out are the binomial distribution. So that's a discrete distribution. That's the only discrete one that I decided to show you. There's a lot of other distributions as well. But binomial is one of the more used ones. Then continuous uniform distribution is basically just all outcomes are pretty much equally likely. So if I went and I drew a histogram, you can see it from my little joke here at the bottom, a histogram of a continuous uniform distribution will pretty much be a flat line because all outcomes are equally likely. If I can just skip back to binomial again, like I said, it's discrete, and it's basically if you have an experiment and each outcome can be a success or a failure. So you define what's a success and what's a failure. So each outcome in the experiment is a success or a failure. There's a fixed number of trials. So let's say, for instance, I have 20 students that I pick at random and I ask, do you drink coffee in the morning? A success for me would maybe be, yes, they drink coffee. So I count the number of successes. And the distribution that we're looking at is how is the number of successes distributed. So what are the chances of me getting 0 successes, 1 success, 2 successes, and so on. Now, normal distribution, like I said, that's the well-known one. It's symmetric around its mean. So the mean, the mode, the median, all of them are here in the center. And that the normal distribution is used a lot. The t-distribution looks just like the normal distribution, but it has heavier tails, which means the values are actually more spread out. So yeah, the t-distribution, we deal with a bit more uncertainty in that. So that's why we do t-tests when we have to estimate extra parameters, and we'll get to that in tomorrow's class. So I will do another poll just now about about hypothesis testing, just so that I know exactly what we need to look at tomorrow. And I want some participation in the chat for that as well, please, just so that I know what tests you guys would like to look at specifically, but we'll get to that just now. So when we work with distributions, it's actually very straightforward working with the continuous distributions. The discrete distributions, there are some tricks that you just need to keep in mind. And the biggest trick that you need to keep in mind with that is that when we calculate probabilities from a discrete distribution, whether I include a value or not in my calculations does make a difference to my answer. So if I say, for instance, I want the probability of my variable being less than 15, or less or equal to 15, those two answers are not going to be the same for a discrete distribution, because whether I include that 15 as an option that I'm interested in makes a big difference. When we're dealing with continuous distributions, we don't need to worry about that kind of thing. So for instance, just to illustrate that, what I mean by that is if I have a number line and I want the probability that x is less than 15, I'm actually asking about what's the chance that x is either 0. So my number of successes is either 0, 1, 2, 3, anything up to and including 14, not including 15. Whereas, and each of these will have a non-zero or very likely a non-zero probability attached to it. So if I then calculate the probability that x is less or equal to 15, you can see there's an extra probability that's added in there. So it will make a difference to my answer. So that's just in short what we need to consider. So yeah, that's the basic idea with, or the biggest trick to remember when you're dealing with discrete distributions. So I'm a bit worried about those of you that haven't done, or have you all done probabilities at least from different distributions? So basic first year statistics, first semester, first year. Okay, good. So then you should be able to follow this. So I'm not going to make it complicated at all. We will do a little bit of simulation today as well, but you'll just to show you what you can do in R with simulations, or that just how easy it actually is. So don't stress about it. And if you have questions after the class, like I said in the last lecture, I'll give you my email address. In the meantime, you can post questions on Slack and I will answer there for you as well. Now, before we move on, I just want to do this poll because I don't want to lose anyone at the end and then not know. So I want to just know how comfortable you guys are with hypothesis testing, just to know also at what level to aim the class tomorrow. And then in the chat, if you can just let me know if there's any specific hypothesis tests you want us to look at tomorrow. You can just tell me which tests those are, and I can see how we can integrate them. I haven't set up my class for tomorrow yet, so it's still open for whatever you guys want to get into tomorrow. So if there's a specific hypothesis test that you need for your own research, you can let me know and I can see if I can maybe figure out what functions you would have to use. Yeah, so see, most of you know the basics at least so far. So we're still missing a few people here. We have 6 responses. Okay, 1 person extremely comfortable. So do you guys want to do t-test? I can do t-test maybe. We can maybe look at a chi-square test of independence if you want. So yeah, just let me know which tests you want to look at tomorrow during the course of today's session, and then I will incorporate those. We're still missing about 11 people. And you have about 16 seconds left. Okay, good. Most people seem to know the basics. Okay, awesome. Cool. So let's then go back to R. So I'll just show you the basics here in R of distribution. So you'll see on Moodle, I've already put this script there. I put this there last night. So I haven't really added any code into this specific one, except I think here at the bottom. So I wanted to just show you the basics of the distributions. So firstly, binomial, and you'll see the rest of them follow along the same line. So we have the binomial distribution, which I said is a discrete distribution. So let's just put the NB discrete. So let's say, for instance, we want to go and calculate some probabilities. So we said that the probability that x is less or equal to 15 is not the same as the probability that x is less than 15. So we're going to do two different calculations here. But basically, we need a function now to go and calculate the this probability from. So you can just start guessing and say maybe it has something to do with binomial. So you can see there's a binom test function, which it tells you performs an exact test of a simple null hypothesis. So that's not what we're interested in. We want to calculate a probability. We do binomial. This function also has something to do with a general linear model. So also doesn't seem to be the right thing. So the correct function here, and this is true for all of the different functions that we're going to use. All the probability functions start with P. And if you then start typing binom, you'll see that's how you find your function. So P binom, probability for binomial, has the syntax Q, size, probability, lower tail, log P. So if you want to learn more about that, let's do the question mark and P binom function. And you'll see the binomial functions are in the stats package, which is automatically loaded. So you never have to load this, it will automatically be there. And then it tells you here that there's actually a few different functions you can use. So D binom is it's a density function. I've actually never used it. P binom is the one for probabilities. Q is for quantiles or quartile. Well, quantiles is the right word. And then R binom is the last function that we could use. So that's going to be what we use when we do the simulations. Now, if we look at the arguments, you can have P and Q, or Q and X are your vector of quantiles. It does matter whether it's a capital or a lowercase letter. With R, it is case sensitive. So I think let's just try that. If we do question mark with a capital P, you see it auto-corrected it for me, but I'm going to force it now to do a uppercase. You can see it says no documentation. It doesn't know what function it is. So it is case sensitive. Okay, so in the P binom, it says it wants a quantile. And in the Q binom, it wants a probability. So that's important when we get to that percentile question. Now, size is used here in all of these functions. So that's the number of trials, and it has to be 0 or more. So if you think back to that example I had with picking 20 students to tell me whether they drink coffee in the morning or not. In that case, I've picked 20 people, my sample size is 20, and I'm going to check each of them for whether they're a success or a failure. So that would have been the 20 that I enter. So let's say this is the distribution that I have. So with distributions, if we know the parameters of that distribution, then we can calculate probabilities, we can calculate percentiles, we can do everything we need to do. So for a binomial, my parameters are my sample size, or my number of trials, in other words, and the probability of success in a single trial. So if I use this distribution, a binomial 20 0.34 distribution, it means that I have 20 observations or 20 trials that I'm looking at, and the probability of success for any one of those would be 0.34. There's some other conditions you need to check to make sure it's binomial. I don't want to get into that theory too much today. If anyone wants to chat about that, I'm happy to. But I think the focus for me today is more on how do we use this in R. So for all of these functions, we will have to enter that sample size, or the number of trials. That's what we prefer, as statisticians, we prefer to call it the number of trials. And then prob is the probability of success on a single trial. And it has to be the same. So everyone that we sample has to have the same probability of a success. That's one of the conditions for binomial. And then that log p function, that's if you want to log probabilities. I personally haven't used that, so I won't say too much about that function. And then lower tail indicates whether we want the less or equal to probabilities. Otherwise, and this is very important, it gives us the probability that X is greater than that X value that we entered in our statement. So let's start with the first one. We want to calculate the probability that X is less or equal to 15. So all we do is we say P binom, so probability for binomial. Then we have to give it the quantile we're interested in. And in this case, the quantile is 15. My size is my first parameter, 20, and my probability is 0.34. And then we can indicate there whether lower tail should be true or false. So we want to calculate a less or equal to probability. So lower tail would be true, but by default it is true. So we can double check that. So I'm going to run this and we get our answer there. Now, if I went and I copied this code and I added in there lower tail equals true, you will see we get the exact same answer. So if it's a lower tail probability, we don't need to enter the true there. It's true by default. Now, if we want to calculate the probability that X is less than 15, how would we do that? So you guys must tell me what I need to type. Keeping in mind, this is a discrete distribution. So less than 15 and a less or equal to 15 are not the same thing. So what number should I put as my first argument?
14.
Perfect. 14, and then the rest of it stays the same, 0.34, and there we go. And you can see when we calculate this, we do get a different probability. So probability that X is less or equal to 15 and less than 15 are two different probabilities. Perfect. Now, the probability that X is greater or equal to 12. I want you guys to tell me what to enter here. So how would I approach this? Any ideas? I see a 1 minus. So let's start with a 1 minus. So 1 minus, and I'm guessing then it's P binom. And what do I put here as my first argument? $11. Perfect. Okay, so, and then it's just the 20 and the 0.34. So there we go. And I run that and I get my answer. Anyone unsure why we did this? Or what the logic behind this is? Okay, so I'm going to go back to that number line. And I actually always tell my students, don't be shy to use a number line. Number lines are your friend. So until you're used to, especially if you're not used to working with distributions a lot, drawing a picture or drawing a number line is a very, very useful thing to do. So I know, unfortunately, with the version of PowerPoint that I have, my graphic tablet doesn't want to work very well with this. So it might make some random squiggles across the screen like that one. I did warn you. So yeah, let's just ignore the random squiggles. There's no way for me to control that. So what we want is we want the probability, if I go back to that, we wanted the probability that X is greater or equal to 12. So what I'm interested in is this value, this one, the probabilities associated with all of these. Now we know if we add all of the probabilities associated with all of these outcomes, it needs to add up to 1. So if I say the probability that X is greater or equal to 12 plus everything I haven't marked, which is the probability that X is less or equal to 11, all of this should add up to 1. So if I want the probability that X is greater or equal to 12, then that is just equal to 1 minus the probability that X is less or equal to 11. And that's why I then can go and use here 1 minus that P binom using, let's just write that, excuse the terrible handwriting, 11, and then all the other arguments. Okay, are you happy with that, Zipo? Perfect. So that's only needed really in the case where we're dealing with a discrete distribution. If we're dealing with continuous distributions, we don't need to worry about this kind of thing. So if we go back here, we have that answer. So we know this is the correct answer. Now let's say I don't want to do the 1 minus thing. I want to use the P binom function, and I want to make use of that lower tail argument to do the calculation. What would I type here? So should I type 12? Should I type an 11? Should I type a 13? What do I type as my first argument? And here you should be paying attention to the help file, the bit that I've highlighted. I'm going to just type a 12. Let's see what happens if I type a 12. If I run this, you can see that I am, oh, I forgot to put that lower tail bit. Let's just add that. Lower tail equals false. So my answer should be 0.01535, blah, 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 but I'm getting a different answer. And that is because if I put lower tail equal to false, it's actually calculating what's the probability that X is larger than that first value. So that's what's the help file tells us there. So I need to change this now or adapt because I want greater or equal to 12, which is the same as greater than 11. So I need to make that an 11. If I run that, then I get the right answer. So with discrete distributions, it gets a little bit more tricky just about because you have to think what is included, what is not included. Where with all the continuous distributions, you don't have to worry about that at all. Like you just do the calculation. It's not going to make any difference to your outcome. And I'll explain that just now. So we can do percentiles. And for that, we will use the Q binom function. And let's do that, QBinom. So now the first argument is my probability. So if I want the 92nd percentile, what should I enter as that first argument? Any ideas? Perfect, 0.92. So the common mistake is that people think, oh, 92nd percentile, so they'll enter a 92. But this very clearly states a probability, and all probabilities have to be between 0 and 1. So 92nd percentile, and then again, it's just the rest of my argument. So if you see here, QBinom, it's just my sample size or my number of trials, the probability, and then you can do lower tail equal to true as well if you want, but by default it will be equal to true. So if we do that calculation, you can see that my my function or my answer is 10. So without having to go, if you guys did first year stats, you'll remember the binomial tables probably. I know that's one of the things where students lose the most marks because the tables, yeah, you have to think very carefully about how to use them. This is much easier. You just type it and R gives you the answer. So for continuous distributions, works very much the same. But now we're dealing with a uniform. So we just need the right function. So I'm going to just start typing here. Let's say I want to calculate a probability. And again, I'm just going to guess it, P uniform. So let's just do a question mark there. I'm just going to remove the brackets. And you can see here, again, same pattern that follows. So there's a density function, there's the probability, the quantile, and the random one. The first argument in each case is pretty much the same. And then by default, the minimum is 0 and the maximum is 1. So if I say P uniform, and let's say I use that value that I had there, 12.24, it's going to give me 1 because I've actually specified here that my data is uniform from 0 to 1. So all my observations are expected to be between 0 and 1. So the chances of, or the probability of me getting something less than 12.24 is 1, because why would it not be? It's like everything is between 0 and 1, so it has to be 1. So with these probabilities, we can also go specify, or these functions we can specify in what range to look at. And you can see all the other arguments are the same as before. So if I want that probability that x is less than 12.24, I can just say P uniform, and it made the brackets already, 12.24. And I can specify then I'm interested in the range 15 to 35. So I can type min equals 15, max equals 35, but R is clever enough that I actually don't have to do that. So you don't always have to type what the argument is for. There are times when it's useful doing that, but it by default will think of the first three because they're required arguments. Well, actually in this case, min and max aren't required, but it will assume that that's what you're referring to. If I run this, I can now get a answer that again makes sense, because 12.24 is below my lower limit. We know all my values need to be between 15 and 35. So the chances of getting something less or equal to 12.24 will be 0. So if we wanted to do a different value, let's just say I want the probability that x is less than 15, or let's make it 17.24. We'll just change that to 17, and you'll see now I'll get an answer which is not 0 or 1. So in the same way, if I want a probability from the uniform distribution, which is a right-sided one, let's actually change this to a nicer value. I'm going to make it 18. The probability that x is greater or equal to 18, then again, I just need to enter those arguments, the parameters for my distribution. And in this case, for the binomial, we saw that the parameters are the number of trials and the probability of success in a single trial, where for the continuous uniform, it's the minimum possible value and the maximum possible value. If I know those two values, I can calculate any probability, any percentile I need. And now in this case, we just want to say lower tail equals to false, because I want the upper tail and I can't type apparently. There we go. And I get my probability. Now, percentile, exactly the same as before, except now we use the Q uniform function. And we again say, here we want the 93rd one, so it's 0.93. And our minimum is 15, our maximum is 35. And by default, because it's a percentile, it is lower tail. So if we do that, we get our 93rd percentile. So I just want to show you what happens if we don't make that a probability. If we made that a 93, you can see here that it gives me an error message. So that is normally your sign that you have done something wrong. Any questions about this so far? So while I wait to see if there's questions, any guesses what the function will be for probabilities and percentiles from a normal distribution? So again, for probability, you can just guess it actually. P norm. I'm just going to show you again. So here, by default, for the normal distribution, it will always work with and Q norm, perfect. So it will, if you don't specify the mean and the standard deviation, it's going to work with the standard normal distribution, which has a mean of 0 and a standard deviation of 1. So if I want, for instance, to look at this first question, and I want to calculate, this is a standard normal distribution. So if I want that probability, I can go and say P norm 1.43, and I can say 0 and 1. I can run that. There's my answer. Or I could actually just recognize it's really not necessary to do the extra typing. You can see I get exactly the same answer. So it's going to assume by default that it is a standard normal distribution. So in the same way, you can go using the lower tail equal false, you can go calculate the upper tail probability, and your percentiles, you will also use Q norm. So in this case, we would have used Q norm, and to calculate the 64th percentile, it's 0.64, and we don't need to specify anything else because we know we're dealing with the standard normal distribution. Also much easier than using the old-fashioned probability tables. We still do that for students, but yeah, it's important to understand the concept. But once you do, you can just use R or Excel or whatever you want to use. So, or Python. So then, if we want to calculate these probabilities, here I want you guys to actually tell me what the code would be. So I'm going to just start here with P norm. And then, so I have a X variable, which is normally distributed with mean 35 and variance 25. So my first argument here, I want to calculate the probability that X is less or equal to 27.8. So I think that one is straightforward, 27.8. What do I type next? Yes, Martin.
35.
35, and next?
And Next, it's 5.
Yeah, perfect. You did not fall for my trick. Well done. So why I asked that question was because in the argument, you can see that it wants the standard deviation. And when we write a normal distribution, we write the variance. So it's just the way it works. So this is a, let me just make a note here, variance of 25. If you've forgotten the notation, now it's written here. And that is why when we write it here, we need to just take the square root of that to get to the standard deviation. And then everything else pretty much works the same way. So you can again do your percentiles and all of that. The only trick with the normal distribution is really that you need to remember to give the standard deviation, not the variance in your parameters. So again, parameters for a normal distribution are the ones things that we write in the bracket. So it is mean and variance in this case. Now, the last distribution I wanted to show you is just the t distribution, and this one is the easiest one to guess. So if you just write here PT, so it's the t distribution, there's nothing else to write. So it's actually technically students' t distribution. Everyone just calls it the t distribution. So it's dt, pt, qt, and rt are your options. And you can see here it has something else. So it has the first argument is the same as before. Degrees of freedom you have here as well. And then NCP is your non-centrality parameter delta. So if you're using a non-central t distribution, you can also go specify that. If you don't specify something, it assumes it's not you don't have a non-central parameter. Then you again have the lower tail function. And if you're taking logs, then that's also an option to include there. So I'm not going to go through these because I think you can go and try them yourselves. And if you get stuck on it, you just let me know and we can chat about it. So what I want to move on to now is just the simulations. So does everyone know what a seed value is? Or is there anyone that's unsure about what a seed value is? So you all know what a seed value is, I assume. So to set a seed value here, again, super easy to guess the function. If you just start typing set, you'll get the set.seed one. And you can enter your seed value. I'm going to make my seed value 4. So, I will add something about seed values just now. I just want to show you this set.seed. So you can get more information here about how the seed values work. But pretty much all the times I've used it, I literally just use the first argument. So I just set my seed value. I don't worry about all the other arguments in here. But you can go and if this is important to you, the information is available. I don't even know what this is. Literally the first time I've looked at this documentation. So we can all set our seed values. So you should get the same results as I'm getting if you've set the same seed value. However, we have noticed with our teaching that depending on your version of R, you can still get different results. So if we're all using the same version of R, we should get the same results. I have noticed also if you're using a Mac, and I've seen the same thing with Excel, Mac versus Windows. If you, Mac versus PC, if you use Excel, I've also noticed that even with the same seed value, you might get different results. But it's, yeah, I don't have an explanation for it. But yeah, at least if you use the same seed value every time, you should get the same results every single time. Now, if we want to generate 10,000 values from a t distribution, so the one we've defined up here, I want you to use this to calculate empirical probabilities and percentiles, or the percentile that I've asked for there. And I want you to compare it to the theoretical values above. So I'm going to help you with the, yeah, I'm not sure. I'm going to guess maybe, yeah, I would probably not be the best person to ask for a guess on that. Maybe Benjamin can, well, you guys will probably know more about random number generators than I do. I've just noticed that there is a difference depending on what version of R you're using, that there's some issues there. And like I said, I've noticed the same thing happening with Excel. We've had some massive issues with students getting completely different answers following this exact same process as we did, and they got different random numbers in Excel as well. And we finally figured out it was some versions of Mac. It wasn't even, some Macs gave the right answers, or the same as the PCs, some didn't. So I'm not sure, we've never been able to figure out, but I'm not a computer engineer, so I don't know. So if anyone knows why, please let me know so that we can figure out how to fix it. So I would really appreciate that. Okay, so the first thing I want to do is just generate these values. So let's just call it samp, because we don't want to call it sample because that's a function in R. So I'm going to generate a sample. Let's call it tsamp. So for that, we will use the function that we found earlier, the RT function. So the RT function is, the first argument is what sample size. So we want 10,000 sample observations in our sample. And then our second argument would be our degrees of freedom. So there we have our 13, and I don't have a non-centrality parameters, so that's it. So if I look now here in my environment, I just want to close that up again. You can see here I have 10,000 observations from that T distribution. So we can go view it, same as before. And you can see now it looks a little bit different. So it's stored as a vector of doubles, so it doesn't look as nice as a data frame. You can go force this as a data frame. I don't think we need to spend time on that now, but yeah, you can get the basic idea here. You could also go and print a few of these values if you wanted to. So we have these values, and let's say, for instance, we wanted to, I'm just going to do that first calculation, PT. So I wanted to calculate here theoretically what the probability is of getting a value 5.8 or less. And there's my actual theoretical probability. Now, let's say I wanted to, I don't trust the distribution. I wanted to go and check if this really is the probability. I could do that empirically using this sample that I've just generated. So I'm going to give you guys a few minutes to think about how would you do that. So any suggestions? I'm open to any suggestions you have. Basically, just to explain an empirical probability would be to just say, well, you have 10,000 values. Let's go count how many of these values are less or equal to 5.8. So in the 10,000, I would go and check how many of the values are less or equal to 5.8 and then convert it into a probability. So that's the idea of what I want to do. Now the question is, how do I do it? And again, there could be multiple ways of doing it. So with coding, the important thing is, if you need to go code something from scratch, you want to understand your process first. So you don't think of the code first, you first think of the process. Once you know what the process is, then you start thinking of the code. So I'm open to any suggestions. How would we, for instance, just count how many values are less or equal to 5.8.
Can you try
Yes.
T sum less or equal to 5.8?
Okay, let's see what happens. Okay, so we end up with a bunch of true and falses. Okay, so we have a lot of, let's actually change this to something a bit smaller. I'm just going to make it 2.8 just so that our answer isn't so close to 1. Let's make it 1.8. I haven't actually played around with these values. Yeah, let's make it 1.8. Okay, so this is equal to 1.8. Okay, so there we have now a few more falses in there as well. So what next? So you're on the right track.
So I think, yeah, let's try to use that one to index.
Okay. So we could, I'm
trying to think of.
So I see there's a suggestion in the chat using a for loop to go through and count. You can do that. So you want to basically, Isaac, you're saying we need to count the number of trues, right? So we can actually do this without a for loop. So a for loop it's computationally not as efficient. So there is a more efficient way of doing it without a loop. And part of that is actually on the screen already. So if you think of these trues and falses in terms of ones and zeros, R will interpret a true as a 1 and a false as a 0. So that's a little bit of a hint.
Okay, hello.
Yes.
Okay, I was saying that when you use the for loop, you put a condition that, okay, if our number is less than this, then we should add it, count it as 1. When it's less than this, all the numbers that are less than, just count them as 1, 1, 1, 1. It should be adding to, we get to the last one.
Okay, so let's say, let's make it a counter equal to 0. And then you're saying we do a for loop and we say for each I in, and we know there's 10,000, so I'm just going to type 10,000. You can go count it. So if, so I can't remember how the ifs, yeah, so I just want to see what the syntax is for an if, because it's something I don't actually use very often in R, but it's looking for something else here. Can't actually remember. Let's actually search here. If
supposed to be if else.
Yeah, let's try the if else. There we go. Okay, so there's an if else. So if else, and then the test is what do I type there?
Hello, can we write it if our I think we are looping through the is it the T sum? Are we? I guess we are looping through the T sum.
Yeah.
So
is less than 1.8.
I think it's supposed to be if I is less or equal to 1.8, not T sum.
Okay, but remember I is just an index. So I is going to, yeah. So if we do,
it's an index.
Yeah.
All right.
Yeah. So, and this actually forgot, it has to be I in 1 up to 10,000. So we have to, unlike with Python, we have to give it a starting point and an end point. Otherwise, we're going to run into some issues here. So you have to give a range of values. So we're going to go through each of these observations, check it against 1.8. And if it is less or equal to 1.8, then we are going to say counter And let's see if this works. Plus equal 1. I don't know if this will, no, it is giving an error here. So it doesn't like that equal. So let's try, I just want to see if this works. Like I said, I don't actually use if-else statements at all. Let's see if this works. So we'll have that. No, there's otherwise there's let's just try the same thing but with a 0. And if there's anyone here who does have experience with these loops in R, feel free to let me know where I'm going wrong.
Hello.
Yes, hi.
I have a suggestion. Can we write it just a simple one? If into brackets that T sum, then the indexing comes in, then we close it, and then we said if I wish you could write so that I can follow.
Yeah, okay. So you want us to, I'm just gonna write it there.
If
yeah,
yes, into brackets.
Yeah.
The T sum that will bring the index.
Yeah.
I.
Yeah.
Less or I think less, is it less or equal to 1.8?
Yeah, less or equal to.
Then we bring the curly bracket. Let's bring the curly bracket on down.
Sorry, then we
bring the curly bracket. Then we'll,
okay.
Yeah, after that one. No, not inside. Outside.
After. Okay.
Yeah. We bring that. Then let's break it. Okay. Or then we can bring the count is equal to count plus 1.
Okay, let's do that and see if that helps. Okay, so I've run this first bit of code already, and it did give us a sensible answer. So it gave 9580. So I'm just going to run this now and see if it works.
I think you should comment yours.
Yeah, I'm only running. Yeah, I'm only running this last little bit. So I'm just
okay.
Yeah. Okay, so if I run that, it gives me 1. So that one doesn't work. It doesn't like that one. It did like this one though. So let's see if I run that one. You can see there I'm getting 9,580, which if we divide that by 10,000, that does give us, this answer was very close to that. So that answer I'm going to think I trust. This one doesn't seem to work. So you can go and check if you can get this one to work. I see we are getting close to the end of the time. So I want to show you the other method. Check how to fix this. So this is, I want you to try and see if you can get it to work as well, and then we can see at the beginning of the next session how that works. Now, the way that I was thinking of doing it is to say, actually, we're going to end up with a bunch of 0s and 1s. So I want to sum all the trues. So I want to sum all the 1s. So I can just say sum of all of these values. So if I run that, you can see that that actually gives me the 9580, which is much less computationally gone blank on the word now, intensive than a for loop. So if I think in general, that's what I've learned anyway. If you can avoid a loop, avoid it if there's a more efficient way of doing it. So this is personally the way I would have approached it, and then just dividing it by the 10,000 to get the probability. So that's how I would approach it. It helps if you type enough 0s. So then I would have gotten my empirical answer that way. So in R, you can often do it in this way. You don't always need to use a loop. So I'm just going to write here method 2. That's another way you can do it. And then if you can find a way to make this if statement work, please let us know in the beginning of tomorrow's session so that we can learn another way of doing it. And then I want you guys to also try and just figure out how would you get the 74th percentile. So that's going to be homework. Any other questions at the moment? Okay, so then the last thing I wanted to show you is just if we wanted to, we've just generated a vector with values now, we can also do it in a matrix. So I can create a matrix in the way that I've done here. So it's just calling the matrix function, and here I've done a matrix filled with NA values. So it has 15 rows, 5 columns. Now, I could also replace that NA. Let's say I wanted to do the or generate from this T distribution again. I can just say here that the number of observations I want is 15 times 5, whatever that is, and I want this to be from a distribution with 13 degrees of freedom. So if I run that, you can see it will generate these values for me and place it into this matrix. So it will generate however many values I need, and then it will just split it into 15 rows, 5 columns. And I've specified my distribution. So that's an easy way that you can do simulations. So second bit of homework that I want you to just go and try and challenge yourselves is I want you to see if you can calculate, find a function to calculate the average for each of the rows and the average for each of the columns, if there's an easy way to do it. So that's just a little bit extra. I'll go and type it in and then I'll upload it on Moodle for you. And I think that's everything I had planned for today. I don't know if there's any questions.
Hello, Prof. Chris.
Hi. Yes.
Yeah, I think the assignments, the assignment in the exercise is just for us to try our hands on, not for submission.
Yeah. No, it's not, you're not getting marks for it. It's just to experience it and see if you're getting stuck anywhere, and then I can help you out if you are. But yeah, I'm not marking them.
Okay, thanks so much. I like your way of teaching.
Thank you. Thank you so much. Any other questions or comments? Glad you enjoyed it, Eric. Anything else before we end?
Yes, a little bit quiet, maybe for Monday morning quiet.
Very Monday morning quiet.
Okay, Christine, I think I just need to thank you. It was very interesting and very nice lecture. Thank you very much. So I will participate that in the afternoon we're going to have a lecture on the machine learning for the bioacoustics, and Christine will continue tomorrow with her lecture. So kind of the timetable for this week is a little bit different from the last week. So I invited to all the lectures. Okay, thank you very much, and hope to see you all in the afternoon. Thank you.
Thank you. Bye.
Bye-bye.